Here's what you're about to find out. Why engineers have to let rock move before they can control it. Where the deepest place any human has ever truly worked is located. What can leave a boring machine trapped inside a tunnel forever? And how a flame could one day replace the drill bit underground. Right now, somewhere under your feet, there is probably a tunnel. It may be a subway line, a sewer, or a fiber optic route beneath a city street. For decades, engineers have been asking one question. How far down can you actually go? Not in theory, in practice. The answer is more complicated than most people think, and it keeps changing. Most urban tunnels sit about 10 to 30 meters below the surface. That is the comfortable range. It is shallow enough for engineers to understand the rock, handle groundwater, and get workers out if something goes wrong. The London Underground, opened in 1863, runs at depths like that. So does much of the New York City subway. Reliable, familiar, and well understood. But those tunnels are not the frontier. The deeper you go, three forces begin to dominate. First is rock pressure. The weight of everything above compresses tunnel walls until even reinforced concrete can crack. Second is heat. Earth gets roughly 3 degrees Celsius hotter for every 100 meters of depth. At 1 kilometer down, the air can become dangerous without cooling. Third is water. Groundwater follows gravity, and gravity always wins. So there is a natural ceiling, or rather a floor, to how deep a tunnel can go before it becomes a crisis. Yet engineers have been pushing that boundary for more than a century. The story runs through coal mines in South Africa, particle accelerators in Switzerland, and a highway project in Norway that forced the world to rethink underground construction. The deepest place any human has ever worked day after day is roughly 3.9 kilometers below the surface. That is the Imponing gold mine outside Johannesburg. Workers ride cages for more than an hour just to reach the active face. Rock temperatures at that depth exceed 60 degrees Celsius. Without heavy refrigeration, no one could survive a shift there. And the mine still goes deeper. But a mine shaft is not the same thing as a tunnel. A shaft is a vertical hole. A tunnel is a horizontal or inclined passage designed for repeated use, movement, and infrastructure. That difference matters, because the engineering of a true deep tunnel is much harder than sinking a shaft. This is why a deep tunnel has to be designed as a living system, not just a hole in the ground. It needs ventilation, drainage, power, monitoring, access routes, and a lining that can tolerate movement without failing. If one part is undersized, the whole project can stall. To understand the limit, you have to understand how rock behaves at depth. Near the surface, rock is brittle. It fractures in patterns engineers can predict. But below about 500 meters, the behavior changes. Rock begins to creep. It flows slowly. It closes around excavations over days and weeks instead of years. This is plastic deformation. It does not announce itself. A tunnel that looks stable on Monday can show serious wall movement by Friday. In shallow work, engineers bolt the rock and it stays put. In deep work, the bolts themselves can get swallowed as the walls keep moving inward. Managing this deformation is one of the central problems of deep tunnel design. The Gotthard Base Tunnel in Switzerland is the longest railway tunnel in the world, stretching 57 kilometers through the Alps after 17 years of construction. At its deepest point, it lies about 2.3 kilometers below the mountain peaks above. That depth produced rock temperatures around 45 degrees Celsius at the boring face. Workers rotated through short underground shifts. The project cost roughly $12 billion. The Gotthard project ran into something engineers call squeezing rock. It is a severe form of plastic deformation where the tunnel bore can shrink measurably within hours of excavation. Teams working through weak geological zones found the mountain pushing back with forces equivalent to hundreds of tons per square meter. The solution was not to fight the movement immediately, but to allow a controlled amount of deformation and then re-excavate. That sounds inefficient until you remember the alternative. If the ground keeps moving and the lining is too rigid, the tunnel can fail faster than crews can repair it. In that sense, a little controlled damage is safer than pretending the rock will behave. That approach, let the ground settle first, then reinforce it, sounds strange at first. In many branches of engineering, you resist force directly. In deep tunneling, you often have to accept it before you can stabilize it. That principle comes from the new Austrian tunneling method developed in the 1960s. It treats the surrounding rock as a partner in the structure, not just an obstacle. Let the rock reach equilibrium, then lock that equilibrium in place with shotcrete and steel. By the 1970s and 1980s, this philosophy spread through major tunnel projects worldwide. But it still had a hard limit. The deeper you went, heat became dangerous to both workers and equipment. Tunnel boring machines are massive rotating cutterhead systems that do most modern excavation. They are enormous mechanical drills. The biggest are more than 15 meters in diameter and about 300 meters long. A single machine for a large project can cost between $20 and $80 million. When one breaks down at depth, you cannot simply pull it out. You repair it underground or abandon it. Several TBMs have been left buried because recovery would cost more than replacement. The machine used on the original Hallandsås tunnel project in Sweden became trapped when the surrounding clay turned fluid under drilling pressure. Another TBM from the Caracas Metro sat sealed in a tunnel for years. These machines can become fossils inside the infrastructure they were meant to create. Heat management is not just about human safety. It is also about keeping electronics, hydraulics, and controls working. On the Gotthard project, engineers pumped chilled water through pipes in the tunnel walls ahead of the boring face. Underground refrigeration plants were used to hold the work face below 28 degrees Celsius. Water pressure is the other constant enemy. Below the water table, groundwater pushes into any crack or weakness in the lining. At 500 meters depth, hydrostatic pressure is about 50 bars, or around 50 times atmospheric pressure at the surface. A leak at that level is not a drip. It is a jet. At even greater depth, that pressure does not just make sealing harder, it changes the entire excavation strategy. A tunnel that is dry near the surface may need a pressurized face, stronger linings, and very slow advance to avoid a sudden inflow. Historically, engineers managed this with draining or pressurizing the tunnel itself. Pressurized tunnel work, known as compressed air excavation, was used as early as the 19th century for underwater tunnels. Workers entered airlocks where pressure matched the surrounding water pressure. It worked, but it created a second problem. If workers decompressed too quickly, nitrogen bubbles formed in the blood. That condition, decompression sickness, became known as the bends after early tunnel work in places like the Brooklyn Bridge project in the 1870s. Modern tunneling has largely replaced that method with slurry shield TBMs, which hold pressure at the cutting face using a pressurized mix of water and bentonite clay. Workers no longer breathe compressed air during normal excavation, but when a cutter needs to be replaced at the front of the machine, someone still has to enter a pressurized zone. Those workers undergo long decompression schedules that can take more than a day. By the early 21st century, the practical depth limit for a true operational tunnel was around 2 to 3 kilometers of rock overburden. The Gotthard Base Tunnel was pushing against that edge. The answer may come from fields outside civil engineering. Some of the most useful recent developments in deep tunneling have come from physics. CERN near Geneva has been building underground tunnels for particle accelerators since the 1950s. The Large Hadron Collider runs in a tunnel 27 kilometers in circumference, about 100 meters below ground. That is relatively shallow, but CERN's proposed future circular collider would require a tunnel 91 kilometers in circumference, with some sections 300 to 400 meters deep. The depth would not break records, but the scale would be enormous, roughly 10 times the excavation volume of the Gotthard project, making it one of the biggest underground civil engineering efforts ever proposed. Meanwhile, the private sector has been trying a different approach. The Boring Company was founded in 2016 with the promise of reducing tunneling costs by a factor of 10. Civil engineers found the claim ambitious. Tunneling costs in the United States had become some of the highest in the world. The Las Vegas Loop, a network of tunnels under the Las Vegas Convention Center, opened in 2021. It runs at about 9 meters depth and uses modified Tesla vehicles in a single-lane tunnel roughly 4 meters wide. Critics noted that the scale was nowhere near the grand vision originally suggested, but the cost per mile was much lower than American subway benchmarks. The company's most notable technical goal was speed. Its ProofRock TBM was designed for faster launch and faster boring. Conventional TBMs can take months to assemble and commission underground before cutting a single meter. Proof rock was meant to begin boring within 48 hours of arriving on site. That matters because mobilization costs, not the excavation itself, make up a huge share of tunnel budgets. But cost reduction and depth are different problems. Making tunneling cheaper does not automatically make it deeper. Deep tunneling needs large diameters for cooling and support systems, plus slow, careful advance so engineers can monitor how the rock responds. There is another issue that almost never gets enough attention: rescue. If something catastrophic happens at 2 kilometers depth, the time available to reach workers is measured in hours, not minutes. The San Jose copper mine collapse in Chile in 2010 trapped miners at 700 meters depth for 69 days. Heat makes rescue even more difficult. Standard firefighting equipment begins to fail above 60 degrees Celsius. Breathing gear has limited duration. Rescue vehicles cannot carry enough cooling capacity to operate for long at extreme depth. Every emergency model for deep tunnel incidents leads to the same conclusion. The deeper you go, the smaller the rescue window becomes. At some point, it approaches zero. Imagine the deepest operational tunnel in the world. Not a shaft. A real engineered passage, ventilated, lit, monitored, and used for rail or road access. The air at the workface is kept at 28 degrees Celsius by refrigeration plants running day and night. Only the low hum of cooling fans and the faint sound of rock under stress remain. That microseismic activity is one of the most important monitoring tools in deep tunnel engineering. Sensitive geophones are embedded in the walls to detect tiny fractures before they grow. Engineers track thousands of events every day, most harmless, some warning of instability. The theoretical lower limit for a maintained tunnel is still debated. Some rock mechanics researchers argue that the practical engineering ceiling is around 5 kilometers of overburden. Below that, the combination of stress, temperature, and water pressure makes sustained human access almost impossible with current technology. That may sound far away, but the Mponeng mine is already beyond 3.9 kilometers, and mining companies are actively planning access to ore bodies at 4 and 5 kilometers depths in South Africa and Canada. Those will require tunnel-like infrastructure at depths no engineered passage has yet reached. Researchers have also explored radically different drilling methods. A paper from NIT in 2020 proposed flame jet drilling, which uses extreme heat to vaporize rock instead of cutting it mechanically. The idea was tested in the 1960s but never scaled. The argument is that with modern materials and control systems, flame jet drilling could eventually reach depths and speeds that rotating cutter heads cannot. That matters because geothermal energy becomes a major prize at depth. At around 5 kilometers in many continental regions, rock temperatures exceed 150 degrees Celsius. If you could drill reliably to that depth anywhere, you could tap into an enormous and steady source of power. Some groups are trying electromagnetic drilling concepts that use focused energy to melt or vaporize rock. Their targets are ambitious, with projections that sound almost impossible. Skeptics point out that deep rock is a brutal environment. Still, even the skeptics agree that if a version of the technology works, it would change the conversation about how deep a tunnel can go. The deepest borehole ever drilled, the Kola superdeep borehole in Russia, reached 12.2 kilometers. It took 24 years from 1970 to 1994. At that depth, rock temperatures reached about 180 degrees Celsius, far hotter than expected. The project was abandoned not because drilling stopped working, but because the rock became so hot and plastic that the hole began closing around the drill string faster than crews could react. That is the clearest warning engineers have. The Earth has its own tolerances. Below a certain depth, no material we currently manufacture can withstand temperature, pressure, and chemistry indefinitely. So where does that leave us? The current practical record for a true engineered tunnel that is regularly used and maintained sits around 2 to 2.5 kilometers of overburden. The Gotthard Base Tunnel remains the benchmark. Around 5 kilometers is where many geotechnical models say the engineering envelope begins to close. That does not mean deeper passages are impossible in every case. It means the cost, risk, and complexity rise so sharply that only the most valuable projects can justify the effort. But technology does not stand still. Every major tunnel adds to our understanding of how rock behaves, how machines fail, and how humans cope under extreme conditions. The next frontier is likely to come from a mix of better sensing, stronger linings, faster excavation, and more intelligent machines. That is enough to keep the field moving for years. The next generation of tunnels will probably be deeper, but they will also be more carefully watched, more data-rich, and more willing to negotiate with the ground instead of pretending the ground will obey.